Hello everyone, welcome back to channel. I am Nikhil Kumar.
Let's say you deploy a container and suddenly it can't reach the internet. No errors, no logs, just no network. And when this happens in production, your service is down. This is one of the most common issues, not just in containers, but also in Kubernetes.
In previous video, we built container networking from scratch with pairs, namespaces and bridges. But understanding how networking works is only the half story. The real skill is how you debug it when something breaks.
Let's start with a container where networking is already broken. So in this particular setup, I have already created two containers. So let's try to access the internet. So for that, we can ping the Google IP address. So ping 8.8.8. So as you can see, it fails.
And honestly, this is exactly how real production incidents looks. A developer says, my app can't reach the internet, a pod cannot connect, and DNS is failing. Now, instead of changing things randomly, let's debug this step by step. So whenever networking breaks, I don't start with Kubernetes, I start with the packet.
Because every packet follows a path from container to Veth to bridge to host and to the internet. And if communication fails, so the issue is almost always happening at one of these hops. So instead of guessing, we validate each hop one by one.
And honestly, most container networking issue can be narrowed down using these three commands: ipaddr, iproute and ping. Because these three commands answer three critical questions. Do I have a network interface? Do I know where to send the traffic? And can I reach to the next hop? If you follow this order, you stop debugging emotionally and start debugging logically. So let's apply this now.
So first, does the container even have a working interface? So for that, we can use a IPA command. So IP space A. So here we can see the interface exists. It has IP address and it's up also. So the interface itself is not the problem. That already terminates missing Veth, broken namespace attachment and interface down issue. Now let's test the connectivity to the next hop. Because before reaching the internet, the packet first needs to reach the host bridge. So for that, we can test the connectivity with the bridge. So we can use the ping command. So ping 10.0.0.1. That is the IP address of the bridge. And to verify that, we can go to the host, and if I run ipaddr command, we can see the bridge is having the IP address that is 10.0.0.1. And I have used the same IP address, and let's test the connectivity with the bridge. So if I hit enter, so we can see it's able to reach to the bridge. So now we know container to bridge communication is healthy. That means Veth pair is working, bridge forward is also working, and layer 2 connectivity exists. So the issue is happening somewhere after this. So if the interface is healthy and the next hop is reachable, then the next thing is to verify is routing. So let's see the routing table in this particular container. So if I use IP space route, so as you can see, there is no default route, and that's a huge problem. Because the container has no idea where to send traffic for the external networks. It just knows how to reach its local subnet, but anything outside that, there is no path for that. So the packet never leaves the container properly. So let's prove that using the tcpdump. So if I go to the host and if I use tcpdump and look for the veth1-host and let's press enter here. So right now it's trying to capture the packet from the veth1-host. Now let's test the connectivity with the internet from the container again. So if I go back to the container and if I run ping 8.8.8, so it fails. And if we come back to the tcpdump, so you can notice something interesting. We barely see meaningful outbound traffic because routing is broken before proper forwarding even begins. This is why packet tracing is powerful, and it shows you exactly where the communication stops. So now that we found the root cause, the fix becomes very simple. Let's update the routing table. So for that, let's cancel this particular command and let's go back to the container and let's add the rule in the routing table. So IP route add default via 10.0.0.1. So what this particular command does, for anything outside from the local network, it sends the traffic to the bridge gateway. So let's press enter. So now we have added the rule in the routing table, and to verify that, we can use IP space route. So here we can see it has been added. So now it's time to test the connectivity again, and let's run the same command again, that is tcpdump. So let's run this. So right now there is nothing in this particular output, and if I run the same command, that is ping, so it's working fine now. And if I come back to the tcpdump, now let's look at something very interesting. We are capturing packet directly on the host side Veth interface. So we have used the tcpdump command to capture the packet on the veth1-host. And now when the container side sends the traffic, that is ping, we can literally see the packets moving. So if we come back here, So if you see the IP 10.0.0.2 to the DNS of the Google, and that is the ICMP echo request. So that means this is the ping packet leaving the container. And notice the source IP, that is 10.0.0.2. That's the private IP of our container. So right now we are capturing packet before NAT happens. So this packet already passed through the container network stack, Veth pair and the Linux bridge. But masquerade has not happened yet. So the TCP dump on the Veth interface still shows the original container IP. And if we see the response from the DNS.Google, and it goes to the container IP, that is 10.0.2. So here we can see the response packet coming back from the internet. So this confirms several things immediately. Container can send packet, host forwarding works, NAT is working, and return traffic is working. That means routing is correct. And this is exactly why TCP dump is a powerful debugging tool, because instead of guessing, we can see the packet journey.
Notice something important here. We never guessed, we never restarted random services, and we never changed 10 different configs blindly. We follow the process, and honestly, that's the difference between memorizing command and actually understanding networking. So whenever you debug container networking, always validate these three things: interfaces, routes, and connectivity.
Now here's the important part. This exact same networking flow exists inside the Kubernetes, because Kubernetes does not replace Linux networking. It automates it. So let's map what we build manually to what actually happens inside the Kubernetes cluster. So here we have a Kubernetes pod. Inside this pod, container generate network traffic exactly like a normal Linux processes. So when an application inside the pod tries to call the another pod, access a service, or reach the internet, the packet journey begins here. Now the pod itself does not directly connect to the network. It connects using the Veth pair. Exactly the same Veth concept we built manually earlier. One side of the Veth pair stays inside the pod, and another side is attached to the Kubernetes node networking stack. Now this is where the Kubernetes introduces something called CNI. CNI stands for the Container Network Interface. The CNI plugin is responsible for creating Veth pairs, assigning pod IPs, configuring routes, and connecting pods to the node network. So instead of us manually running IP link, bridge commands, or the routing commands, the CNI plugins automate all of that for us. And depending on the cluster, this could be Flannel, Calico, or another CNI solution. So once the traffic reaches to the node, the packet moves through the node networking stack, just like our earlier setup. So here you can see bridge still exists, routing still exists, and forwarding still exists. And many Kubernetes setups internally uses Linux bridge like BR0 or CBR0. So the node now decides where the packet should go, where it needs NAT, and how it should leave the node. And if the pod is accessing the internet, the node performs the NAT using the iptables or the eBPF depending on the networking setup. So the pod IP gets translated to the node IP, and then traffic reaches the internet. And when the response comes back, Linux connection tracking maps the response back to the original port. So underneath Kubernetes, the traffic flow is still fundamentally the same: Veth, CNI networking, node bridge, routing, NAT, and the internet. So Kubernetes simply automates interface creation, routing, forwarding, IP allocation, and connectivity management. And this is why Linux networking knowledge is so powerful, because when Kubernetes networking breaks, you are still debugging the interfaces, routes, bridges, and packet forwarding under the hood. So even in the Kubernetes, the debugging mindset stays the same. That means follow the packet.
So next time your pod or container has a networking issue, don't guess. Just follow the path: container, Veth, bridge, host, and internet. Once you understand this, networking stops being magical and debugging becomes more predictable. And that's the difference between running command or understanding networking under the hood. So if you found this video helpful, hit like, share it with your friends, and subscribe for more content like this. Thanks for watching. I will see you in the next one.